Hello, my name is Liam, and for this presentation I'll be talking about biodiesels and how you get fuel through transesterification. To start, just a quick review with nucleophiles and electrophiles. Nucleophiles donate an electron pair, shown here, and they're usually shown with a negative, as shown here and here. Electrophiles, on the other hand, accept electron pairs and are usually shown with a positive, as you can see right here and right here. Another thing to review are pi bonds. Pi bonds are electrons and atoms that are in the p orbital, and their lobes on the orbital overlap with the lobes on another atom's orbital. On the contrary, though, there are sigma bonds as well, which are electrons that are in the s orbital and are the result of head-to-head overlapping of atomic orbitals. Pi bonds that are in double and triple bonds are far more reactive than in single bonds as well. Finally, there are factors that influence reactivity. A few of these we should already know, like electronegativity as well as atom size. But there's also inductions, which is the unequal sharing of the bonding electron. As well as there's electron delocalization, which is an electron that steps outside the boundaries of the Lewis theory, making it more reactive. Now we will look at the overall general reaction that occurs to produce biodiesel. You take 1 mole of oil or fat, such as a vegetable oil, as shown here, and combine it with 3 moles of alcohol. As you can see, there's 1, 2, and 3 there. And this overall reaction produces 1 mole of glycerol, also known as glycerin, which is the co-product in this reaction, as well as 3 moles of the biodiesel on this side. And this overall reaction is called transesterification. Looking at this process in more detail, triglyceride, which is here, reacts with 3 methanols using a base catalyst of sodium hydroxide right here. This breaks the fatty acids off from the triglyceride, which are right here, and combines with the methane from the methanol to form the fatty ester, which is the biodiesel. As you can see, the methane from here is also shown here on each one, which is then combined with the fatty acid there to make the biodiesel. The carbon chain left over from the triglyceride, shown in pink here, combines with the hydroxide left over from the methanol, as you can see the hydroxide right here, to form the co-product glycerol, also known as glycerin, as shown here. You can see the hydroxides here on each one, and then your carbon chain from the triglyceride here. I will now quickly go over how this experiment can be done in a lab, and then I'll go over in more detail why this reaction happens. First, you grab your alcohol and your catalyst, and you mix them together and stir them until the catalyst is fully dissolved within the alcohol. You will then grab your oil, which is typically vegetable oil, and heat it to 60 degrees Celsius. Once it reaches 60 degrees Celsius, you will then add your alcohol mixture within it. Once you have the mixture together, you will then start stirring it with a magnetic stirrer for 60 minutes while keeping it at 60 degrees Celsius. You will then let it cool, and you will start to see that the glycerol will separate to the bottom from your biodiesel. You can now remove the glycerol, and you'll be left with your biodiesel in your container. This is typically done through a funnel. I will now explain why this reaction happens. The sodium hydroxide breaks into ions of sodium and hydroxide. The hydroxide abstracts the hydrogen from the methanol to form water, as you can see here, the hydrogen here is taken from the hydroxide here to ultimately form water. This then leaves the methoxy group, as shown here, available for the rest of the reaction so it can occur. I will now explain the overall process in a lot more detail. The carbonyl, which is the fatty acid on your triglyceride, has two electronegative oxygen atoms, which are right here and here, which makes this an electrophilic center. Now the oxygen on the methyl, as you can see over here, has two lone pairs of electrons here and here, making it a nucleophile. Since the methanol is a nucleophilic and the carbonyl is electrophilic, it will donate electrons to then make this compound here. Now before nucleophilic substitution can take place, which is this separating from the rest, the alkyl oxide on the ester, which is right here, must be propionated, which means protons are being added to it. And once that happens, it can separate into your glycerol molecules here, and then your biodiesel, which ultimately just makes your biodiesel or your fuel. And that's how this overall reaction works. Now that we learned how to make biodiesel from vegetable oil, I will go into more detail about biodiesel itself. Biodiesel has a great advantages within the real world, as it can be a possible solution for renewable energy in the future. First of all, it's produced from renewable resources such as plants and corn and stuff. That's how vegetable oil is made. It can be used in existing diesel engines, so there's no need to look at, say, battery-powered engines and stuff anymore. You can revert back to the engines we already have and just use renewable energy, as in the biodiesel. The biodiesel itself produces a lot less greenhouse gas emissions. It can also be, well, it's grown, produced, and distributed locally. The refineries used to make the biofuel is a lot cleaner, and it's biodegradable and non-toxic to the environment. So overall, biodiesel should be looked at more in the future for renewable energy. And that's it for this presentation. I've also included within the references a link to a YouTube video right here showing how the experiment can be done in a lab. And that's it. Thank you very much for watching. Take care.